Welcome to the Electronic Lab 9. In this lab, there are 3 experiments. Before we start to explain the experiment, let's understand the component we're going to use. This one is 2N7000. The internal structure can be modeled as this. You can see that there are diode-like circuits inside. Therefore, you should correctly connect the source and drain. Note the pins for this component. This is CD4007. It contains 3 CMOS inside. The gate and source of the first PMOS and NMOS are connected together. Others are separated. The N-channel P substrate of the NMOS is connected to the VSS pin, and the P-channel N substrate of the PMOS is connected to the VDD pin. We're going to use the first one in this experiment. Note that the pin number of the PMOS. Its drain is at pin 13, gate at 6, and its source and body are connected together and at pin 14. You can use the pin number to know the position of the pins using the graph above. Experiment 1. The current limit is 0.01 ampere. This should be set first in order to protect your MOS element. First, we'll use the 4007 to measure its PMOS. Use 2 different methods to measure the threshold voltage. One is use the multimeter, the other is use this circuit. Then also measure the NMOS using these 2 configurations. We know that the MOS will activate while the voltage from gate to source is greater than VT. Therefore, we can measure the VT by observing if there is current to know when does the voltage reaches VT. Take the NMOS for example. If there are no current passing through, then the voltage of point C should be the same as VDD. When it changes, then the MOS is activated. Using the other configuration, we'll connect the multimeter in the DVM part. Because the internal resistance of the multimeter is large, so when the current passes through the multimeter, we'll consider it as a condition of activating the MOS. Measure the current pass through and multiply it with the internal resistance of the multimeter to get the voltage drop. We'll then consider the VDD minus the voltage drop to be our VT. For example, if our VDD is 10 volt, the internal resistance of the multimeter is 1 mega ohm, and the current passed through is 8.8 microampere. Then we could calculate the voltage drop is 8.8 volt. We can then see the voltage of this point is 10 minus 8.8 equals to 1.2 volt, which we'll consider to be the VT of this MOS. For the PMOS is similar. Only note that the VT of PMOS is negative. The third part of this experiment can be done for bonus point. You can also skip it. Set the RG in all these configurations to be 0 in this experiment. That is, to short them together. Obtain the V-in and V-out curve of the 2N7000 using this circuit and the following conditions. And remember to use DC coupling mode. Then, this is the IV curve of the NMOS. You could use this graph directly or either download it from our website. You can see that the channel length modulation effect is not serious. However, comparing with the PMOS, we can see that the channel length modulation effect of the PMOS is more serious. We can therefore guess that in this CMOS, the channel length of PMOS is shorter than the channel length of NMOS. This is usually correct because normally we hope that in a CMOS, the PMOS component and the NMOS component have the same speed. But the electrons of NMOS have higher mobility than the electron hole of PMOS. Therefore, we have to compensate this via shorter channel length, therefore resulting in this effect. This slide is for the bonus lab. This slide is for the bonus lab. See it for yourself. Experiment 2. We're going to measure the stability of these bias circuits. First, construct these circuits with the configuration shown and adjust the voltage accordingly. Replace the MOS by another one and record the voltage of D, S, G, and ID. The same steps are applied to the other two circuits by adjusting different components. Use the same pair of MOS in order to compare the stability of these circuits. Experiment 3. Construct a circuit and set VDD to be 10 volt, R11 to be 1 kilo ohm, and R2 to be 10 kilo ohm, and R21 to be an 100 kilo ohm variable resistant. Adjust the R12 until VDS equals to 5 volt. And observe the waveforms of both input and output signal and calculate the phase difference. Also obtain the frequency response of the circuit. The concept of it is the same as those in BJT. You'll see that the gain and frequency response will change accordingly to different capacitor values. After understanding the characteristic of the amplifier, adjust the input to get maximum output signal without distortion and record the VI and Vout. Without distortion means that the output signal has not been chopped off. And follow the following steps and complete the experiment to answer these questions. That's all for this lab. Good luck.